Hi all, in this video we will see the step up or down or buck boost converter. The step up or down or the buck boost converter operates either as a buck converter or as a boost converter. So as we already know that the buck converter is a step down converter and boost converter is a step up converter. So here this buck boost converter gives an output voltage that can be either higher or lower than the input voltage depending on the operating duty ratio. So the input and output are DC. Please keep it in mind that the input and output are DC. The figure shows the circuit diagram for a buck boost converter. It consists of two switches S1 and S2, which are the power semiconductor switches, and an inductor L, capacitor C, and then the load. Here, the figure A represents the buck boost converter with a SPDT switch, single pole dual throw switch, and then an inductor and a capacitor. So here we can see that the pole is connected to the inductor, and then there is two throws, T1 and T2. We should keep in mind that for a buck converter, the inductor is connected to the output side. For a boost converter, the inductor is connected to the input side. But for the buck boost converter, the inductor is connected between the pole and the ground of the circuit. As we can see in this figure, the inductor is connected between the pole and the ground. So this is the main difference between the circuit of buck converter, boost converter and the buck boost converter. That is, for the buck converter, the inductor is connected between the pole and the output. That is, between the switch and the output. But for the boost converter, the inductor is connected between the pole and the input. The figure B shows that the SPDT switch is replaced with two switches S1 and S2. Here also we can notice that the inductor is connected to the pole and between the ground, pole and ground. In between there is an inductor, then there is a capacitor, and then the load. So like we discussed in the previous cases, we have two operating regions, one or operating conditions. One is during the D into Ts period, another one is 1 minus D into Ts period. So D into Ts period is actually the on time of switch S1. Like we can see in the figure C, during the D into Ts period, switch S1 is closed and S2 is open. And for 1 minus D into Ts period, S1 is open and S2 is closed. So the figure C shows the operative circuit during the period D into Ts. So we can see that from this figure, during this period, the switch S1 is closed and the current is passing through the inductor. Therefore, we can say that there is a current IL through the inductor. And since S2 is open, the energy which is stored in the capacitor is going to the output, and we can observe that the capacitor current is with an opposite polarity. The capacitor discharges with an opposite polarity. And the figure D represents operative circuit during the period 1 minus D into Ts. So during this 1 minus D into Ts, switch S1 is open circuit and S2 is closed. So the current through the inductor cannot change instantaneously. That means the energy which is stored in the inductor begins to discharge. So this energy will discharge in this direction as shown in this figure, and it has got two components. One component will go through the capacitor, which is the AC component, and the DC component will go to the output. Also here the direction of current flow is in the reverse direction, that makes the polarity of output as negative. There are certain observations for this buck boost converters, or there are certain points regarding the buck boost converter. They are, The first point is the output voltage is of negative polarity. So just like we saw in this figure, here the capacitor discharges in this direction. So the polarity of output is inversed. So that is why the output voltage is of negative polarity. Then second point is when the duty cycle D is having a value between 0 and zero point 0.5, it operates as a buck converter. That is, when the duty cycle is having a value between 0 and zero point 0.5, the output will be less than that of the input. Third point, when the duty cycle is between zero point 0.5 and 1. So the normal values of duty cycle is always between 0 and 1. It is actually duty ratio. So the ratio will have values between 0 and 1. So according to the third point, when the duty cycle or duty ratio is having a value between 0 0.5 to 1, it operates as a boost converter. That is, when the D is having a value between 0 0.5 to 1, the output will be higher than that of the input. Then the next point is the source is not connected to the load. Therefore, it is called an indirect converter. We can see from this figure there is no direct connection between the source and the load. So, in both the conditions, that is in both d into Ts as well as 1 minus d into Ts period, the input as well as the output is not having a direct path. So the source is not connected to the load, so it is called an indirect converter. And the last point is the source current is discontinuous as the current flows only when the switch is on. So we can see that if both the switches are op, we can see that when both the switches are closed at the same time, there is a direct connection between the input side and the output side. But this is not happening for the buck boost converter. Therefore, there is no direct current path or continuous current path between the input and output. Now we will see the waveform which represents the operation of buck boost converter. So like we discussed in the previous case, there are certain signals which we are considering for the analysis. They are voltage across the inductor, which is represented as VL, current through the inductor, which is represented as IL, current through the capacitor IC, then the load current, current through the switches S1, S2, voltages across the switch S1 and S2. So we can see that from this figure, during S1 is on or D into Ts time, during the initial time we can see that during D into Ts time, we can see that S1 is closed and S2 is open. So the entire input voltage is available across the inductor. And of course, during the 1 minus d into Ts period, the voltage across the inductor is equal to the output voltage. So please keep it in mind that during d into Ts period, voltage across the inductor is Vi, and during 1 minus d into Ts, the voltage across the inductor is Vo. And of course, here the polarity is reversed or inversed, so the voltage across the inductor will be minus Vo. We can see that from this figure during S1 or during D into Ts time, the voltage across the inductor is Vi, and during 1 minus d into Ts, the voltage across the inductor is minus Vo. Similarly, during the S1 time, S1 on time, the current through the inductor increases, and now at this point, the current through the inductor cannot change instantaneously, so that it starts decreasing. So that is why the graph is shown like this. So during the initial time, it is Vi by L, because the voltage across the inductor is Vi, and during this time, voltage across the inductor is Vo, therefore the current is Vo by L. During the initial time, there is no current through the capacitor, which is maintained like this, and 1 minus d into Ts time, it is increased by a factor, then it starts decreasing, because the energy stored in the inductor is also decreasing. In this figure, it is clear that during d into ts time, the voltage across S1 is less because it is closed. That is, during d into ts time, this S1 is closed. Therefore, there is no voltage drop across this. But across this S2, the total voltage drop will be Vi plus Vo. That is represented here. Also, during that time, during also in the 1 minus d into ts time, the voltage across switch S1 will be the total voltage Vi plus Vo. At the same time, the Vs2, switch S2 will be closed, therefore there is no voltage across S2. That is, during 1 minus d into ts period, the switch S1 is open. Therefore, the total voltage across this will be equal to Vi plus Vo. At the same time, there is no voltage across switch S2. Similarly, the current through the switches S1 and S2 are also varying, because when the switch is closed, the current through that switch will be increasing. So during the initial time, switch S1 is closed, that is why the current is increasing, and during 1 minus d into ts, switch S2 is closed, but the inductor current is decreasing, so that is represented here. Now the input-output relationship. In order to find the input-output relationship, we have to consider the voltage across the inductor during d into ts as well as 1 minus d into ts. So during d into ts, the total voltage across the inductor will be 0 in all time. The total voltage during the entire time will be equal to 0. Therefore, voltage during d into ts is Vi plus voltage during 1 minus d into ts is Vo. So this is equal to, we have to expand this expressions and then solve for Vo. Finally, we will have Vo is equal to minus Vi into d divided by 1 minus d. The derivation is not important, but you can try by yourself. Similarly, the inductor value, like the previous cases, the inductor value L is equal to Vo into 1 minus d divided by delta IL into Fs, where this delta IL is the current ripple and Fs is 1 by Ts. Therefore, the delta IL is equal to Vo into 1 minus d divided by L into Fs. Similarly, the capacitor value C is equal to IO into d divided by delta Vo into Fs. This delta Vo is called the voltage ripple. Therefore, delta Vo is equal to IOD divided by C into Fs. So that is about the buck boost converter. So from this equation, that is Vo is equal to minus Vi into d divided by 1 minus d, we can say that if the duty cycle d is having a value between 0 and 0.5. As an example, we will consider, let Vi is equal to 2 volt and d is equal to 0.2. Vi is equal to 2 volt and d is equal to 0.2. So when we solve this equation for Vo, we will have 2 into 0.2 divided by 1 minus 0.2, which is equal to 0.8 divided by 0.8. So we will have a value which is equal to 0.5. 0.5 is less than 2 volt, and of course there is a negative symbol because of the inversion of input and output, but here the output voltage is lesser than the input voltage. And now consider the duty cycle is between 0.5 and 1. So we will set that the D is equal to 0.6 and input voltage is 2 volt. So we have 2 into 0.6 divided by 1 minus 0.6, 0.4 divided by 0.4. So we have 3. VO is equal to 3. That is, when D is ranging between 0.5 to 1, we will have the output voltage which is greater than the input voltage. So that is how the step up or step down converter works. VO will be infinite when D is equal to unity. These are the points of buck boost converter. Thank you.